Here we will talk about the last of the electrophilic aromatic substitution reaction types. This is Friedel-Crafts acylation. Now here's a reminder, an acyl group is something, the squiggly line just means this is where the acyl group is bonded to something else. You have a single bond to a carbon that's double bonded to an oxygen and bonded to an R group. So this is an acyl group. Acyl groups are a part of a lot of different functional groups that we'll talk about. So in acylation, we're adding an acyl group to an aromatic ring. And so let's do our general reaction scheme. As always, starting with benzene, highlighting a hydrogen. And then we use acetyl chloride, which is where the acetyl group or the acyl group is bonded to a chlorine. Acetyl chloride is when the R group is a CH3. That's the acetyl group. So that's what we're showing here. You can extend that R group and have it be a ethyl, propyl, etc. But for this specific reaction scheme, we will keep it as acetyl chloride, so a methyl. And then this reaction must occur in two different steps. And we show that by using numbers over the arrow. So in the first step, you need a Lewis acid catalyst. And so that can be aluminum trichloride or iron trichloride or zinc dichloride. So these are three different catalysts that can be used for this reaction. So that's step one. And in step two, you have to add water. And these two steps have to happen separate from each other. So this means you would add the benzene, add the acetyl chloride, and then add your Lewis acid reagent to the same beaker. Let that reaction carry out. And then when that reaction's done, you add the water, and then you get your final product. Okay, and the product for this reaction is now we have the aromatic ring where instead of the hydrogen, that's now substituted by the acyl group. This molecule is called acetophenone. Just a reminder, this group here can change for different acylation reactions. For this specific reaction scheme, I chose acetyl chloride, but you can see different ones. And then acetophenone, this molecule is a type of ketone. We'll talk all about ketones later in the semester. Okay, so let's talk about how this reaction occurs. We have the same first step, generate electrophile. And I'll show this with aluminum trichloride, but the process is similar if you're working with iron trichloride or zinc dichloride. The interaction occurs between the acetyl chloride and the Lewis acid. And when you have this molecule in the presence of a Lewis acid, like aluminum trichloride, the carbon to chlorine bond actually breaks. So this occurs through really all in the same step. We have electrons from the oxygen will create a triple bond between carbon and oxygen, and the chlorine, the electrons from that chlorine to carbon bond, will now be bonded to aluminum. So the chlorine leaves the carbon and will be bonded to aluminum. And this generates an acylium ion, where we have carbon triple bonded to oxygen, and then that's still bonded to the R group. This is the acylium ion. And then aluminum tetrachloride is a byproduct. The acylium ion, this is a parenthesis, is our electrophile. That positively charged oxygen is pulling electron density away from the carbon. And so that carbon is electrophilic. And that's how we can create that new bond to that carbon, by using this as the electrophile. So step 2, we use our electrophile to form the carbocation intermediate. We'll start with the benzene ring. We add the acylium ion. So we have an electrophilic carbon, wants electrons. We have electrons and pi bonds in the aromatic ring. And so electrons from the pi bond will create a single bond to the carbon. And one of the pi bonds in the triple bond between carbon and oxygen will break, and so oxygen can own those electrons and become neutral. So this forms our carbocation intermediate. We have carbon double bonded to oxygen, bonded to that R group. We have a hydrogen still on that carbon, and then here we have our carbocation. This is, of course, stabilized by resonance. And in step 3, we remove the beta hydrogen. And this reforms the aromatic ring. To remove the beta hydrogen, this is the same as the previous Friedel-Crafts, the alkylation reaction that we looked at, where we have this aluminum tetrachloride, and that will be used, one of the chlorines will be used to remove the hydrogen. So electrons from the bond between chlorine and aluminum will then be used to create the chlorine to hydrogen bond. Then the electrons in the bond between the carbon and the beta hydrogen will reform the pi bond. So we have pi bond reformed, we have the acyl group added to the aromatic ring, we have HCl as a byproduct, and we have the catalyst reformed. So we have this product, we have the desired product here, but we haven't added any water yet. And if you remember that is one of the reagents in the second step. The reason we have to add water is because ketones, which is the product that we've created here, ketones are weakly basic. So if we have that basic molecule in the presence of a Lewis acid, that ketone is now going to interact with the aluminum trichloride, and then we don't have our desired product anymore. So if we have our product here, let's just see what will happen if we don't add water. Well, with the basic oxygen and the Lewis acid aluminum, this oxygen will create a bond to the open shell aluminum. And so some of the products will then be a Lewis acid base complex, which is not what's desired. So that's a Lewis acid-base reaction that's possible with these products. So in order to prevent that, we add water and when we add water, I'm not going to show the full mechanism, but really what occurs is we have our desired product, the ketone, we have, instead of aluminum trichloride, we have aluminum trihydroxy. And then we would have 3 HCl molecules as well. So the water is needed. Oh, I forgot to write that on the arrow, that we add water. And that's needed to isolate the ketone, which is our desired product. Without the water, we would have both the ketone and the Lewis acid-base complex present. You would really need to add water after the catalyst has been used to produce all of the product, because once you add water, we no longer have our catalyst present. It's not AlCl3 anymore, it's AlOH3, which doesn't really react the same as AlCl3. So here's the reaction that we use to add an acyl group, which has a carbonyl. The carbon's bonded to a alkyl chain. So this is how we add that to an aromatic ring.